Bismillah ar-Rahman ar-Rahim. Good morning, everyone. Today is 8 lectures of advanced artificial intelligence prepared for the students of master studies in Wasit University, College of Computer Science and Information Technology. And today is 27 April of 2025 year. We continue with the lecture 6 that focuses about building control algorithms for state space search. We will explain by using example about using chess player or chess games, and we select one of these pieces, knight's tour problem. In this example, we illustrate the implementation of the control and using machines to explain how we can get the parts of the knights in the board. And this board example about 5 by 5 box, but we will illustrate more simple in this example and use pure dimension. This dimension will be 3 by 3 to explain this. In this game of the chess, knight can move two squares either horizontally or vertically, forward one square in orthogonal directions, as long as it does not move off the board. For example, this time when we moving two boxes and one orthogonal direction, 1, 2, and the third will be moving to be orthogonal to this direction. And in this place, when we decide 1, 2 in the vertical line and one line or one box to be orthogonal about this line, like this, and so on. Thus, there are the most 8 possible moves that the knight may be make. The knight's problem seems to find series of legal moves in which the knight lands on each square that chessboard exactly once. And the example we use in this chapter is a simplified version of the knight sur problem. It takes whether there is of legal moves, series of legal moves that will take the knight from one square to another, reduces size 3 cross 3 chessboard. Now this figure 6.6 shows 3.3 or 3 cross 3 chessboard with each sequence labeled with integers between 1 until 9 number. It's like this: 1, 2, 3, 4, 5, 6, 7, 9. 9. This labeling scheme is used instead of more general approach of giving each sequence row and column number in order to further simplify the example. Like this, for example, beginning of the one knight, when he is landing in this place, when he wants to move it, he have 2 places, either in this place or either in this place. 1, 2, and orthogonal line, this like this 6. Thus, the first location will landing in the 6th box. or 1 to this orthograph, and this order to 5 and 8 will be the vertical. Thus, the possible places that can visit it or moving from 1 square either to 6 square or 8 square. And for example, when he landing at 4 square, this is have two choices. Either this is place 3 or this is place 9. Because we 1, 2, and the other graph, this is 9. This state space we can represent it by using the predicate calculus, and the name of the predicate called move. And the arguments, 2 arguments. The first argument represents the landing space or the start space, start box, and the other argument represents the target or the goal where he go to. For example, move 1, 8, 1, 8. Move represents the start space 1, and 8 represents the target. And move 1, 6, 1, 6, that represents, this predicate represents start space, start box is 1, and the target or the goal is the 6th place. And so, move 2, 8, 2, 7, move 3, 4, move 3, 8, and so. Now, because of the reduced size of the chessboard problem, we simply enumerate the alternative moves rather than develop general move operators, as like this. The general or legal moves on the board are being described in the predicate calculus. It's like this, using the predicate called move, this like this, and the parameters starting point and ending point, starting point 1 and ending point 8, sequence of the legal move. For example, moving 1, 8 takes the knight from the upper left corner of the crossboard to the middle bottom row, because we have column and row. Therefore, move 8, 1 to 8. That move takes knight from the upper left hand corner to the middle bottom row. Thus, the predicates on this figure, figures 3.6, enumerate all possible moves of a 3 by 3 chessboard. Now the 3 knight sword problem may solve it with the production system. Now we will be implement this in the production system, because we maybe discussed the production system in the first lecture. Now we implement this example by using production system. And production system, maybe you recall this, consists of 3 parts. The first one is the working memory and action part, or rule part, consists of 2 parts: conditions, then action, and recycle action by using which one of them will be firing, thus called firing rule. Now each move can be represented as rule whose condition is the location of the knight on the particular squares, and whose actions move the knight to another square. Now 16th 16 prediction presents as in table 6.1. Present all possible move of the knights like this. Now the 16th rule represents the all possible rule can be used to produce the action after applying this in the particular condition. For example, first rule consists of two parts, conditions and actions. The conditions, if knight on the square 1, then it will be moved to the square 8. And for example, in the 12 rules, if the knight on the square 7, the movements will be at the location of the 6 square, and so on. Now, we next specify the recursive procedure to implement control algorithm for the problem or production system. For example, path X will unify only with the predicates such as path 343 and 88. This will be unified or will be true when the two arguments have the same value. For example, path 33 or path 55. It will be true. A divided design termination condition. If path X does not succeed, we will use the projection rules for the possible next state and then recursion. If we get this condition, that's first arguments equal to the second arguments, it will be stop the conditions or stop the algorithm. If not, we will use the recursion algorithm to recur the operation by using another new x, first x1. We look at the production, and the general recursive path definition is then given by the predicate calculus formulas. The predicate calculus, that's equivalent to the recursion procedure, consists of the two parts. First part called the fact or axioms. For example, for all x, path x. This fact will be true when x equal to x. That means two arguments the same. For example, when we want to move from one location to the 9 location, now the first argument 1, the second argument is 9. We will stop the algorithm. That means implement or the applying the conditions or get the condition when first one equal to the second one. First one is 1. Second argument is 9. Thus will be recursion or be repeat the operations and change the first arguments until I get the first argument equal to 9, because the first one is 1, and continue updating the rules, and I get x will be equal to the 9. Thus, x will be equal to x. This happen when I continue updating the working memory of the protection system. That's the main operation. I will work about this. I will continue updating the working memory until I get the first one is equal to the second one. Now, this is the condition will be implemented, or when we get these conditions, I will stop the algorithm. And the recursion will be here. For all x and for all y, path xy imply there exists that where x move to z and the path will be from Z to Y. Here, Z will be changed Z here, and will become in the path X will be Z. Will be true, move X for Z, Z, the other locations. Here will be the Z will be changed by X in the path. Thus will be X will be Z. Now the other part, path for all X and Y, path X, Y, like there exists that move X, Z and path Z, Y. This for changing Z and X in the path predicate. Now we were talking about the working memory. That is the main part of the production system. Working memory, the parameters of the recursive paths predicates contain both the current birth states and the goal states. The working memory consists of two parts: goal states that I will want to reach for it, and the current state after updating. Thus, the working memory will updating always either I not contain or not reaching the stock conditions. The control regime applies rules until the current states equals the goal states and then halts. A simple conflict resolution scheme would fire the first rule that did not call search to loop, because the search may be lead to the dead ends from which every possible move leads to the previously visited states and thus a loop. I think you remember in the search algorithm, in the forward or the backward, in any one of them, we use two lists, open and closed. And we use the closed to guarantee the don't reaching the looping. Here we will use the working memory to guarantee not reaching the looping operations or get stuck in the looping operation, from which every possible is to previously visited state and thus a loop. When particular state was visited, it will be prevented from selection, that not firing. The control regime must also allow backtracking. Now, these operations or the implementation of the production systems by using 16 rules, and we will illustrate the figure of the working memory and the rules parts called conflict sets, that mean rule, and the firewall. In the first one, in the first iterations, the current states that nights landings in the first square, that means one square, and we want to go to the second square, from one to second squares. This represents the operations of solving this problem. How can I get the path that reach me from the first place, that when he was landing at the location 1, and visiting other locations until I reach the location 2. In this space, which rules will compatible with the 2 places or the 2 conditions? Which rule? I see for these rules, which rules begin from the 1 states and ending to 2 stores. I will focus about the starting point only. Starting point 1. Which rules that starting with the 1? Rule 1, square 1, and rule 2 either also square 1. Thus, I will use 2 rules. First rule, I said rules, and written in the complete text. 1 rule and 2 rules. Thus, I will select first one to be fired. The first one, I will write fire rule, first one. Now, implement the first rule. When implement first rule, when the knight on the square 1, the knight will be the square 8. Now the new locations will be 8 square. This location will be updated or update the working memory. Working memory was first location, will be updated to the 8 location. Become 8 because the result of the rules 8. Now will be right 8. Now, which rule compatible with these conditions? In other words, which rules its conditions contains 8? Now looking for these rules where this rule and this rule. 13 and 14. Rule 13 and rule 14 contains the 8 location. Now will be write 13 and 14, and we will select the first one as firing rule. This is writing 13. Now implement the 13 rules. 13 will be knight from square 8 to square 3. The new location will be 3. I will update this location will become 3 from 8 to 3. Now, which rules its conditions contains 3? Looking for 3, 5 and 6. Rule 5 and 6. Now write 5 and 6 as the complete set. I will select first one 8. Implement 8 will be 4. Location 4. I will be updating the working memory, and current square will be 4. And the rule will be conflict sets will be 7 and 8. I will select 7. 7 from knight 4 to square 8 or 9. Would be 9. 9 in the 15 and 16. I will be select 15. Will be moved to the 2 square. Now we become 2. Now the current square equal to the goal square and hold the process. Now I will solve this manually. It's like this. Like this. This consists of 2 parts. First one, current and square is gold. Gold square. This conflict says conflict set and this fire. Fire. And the first one, this is one in the current, and the gold is the 2. Which one would be compatible with the current states? Which one? 1 and 2. This one and 2. I would select first one, this one. 1 will be implements 8. The current state would be in the working memory, because this is working memory. Working memory. This is working memory. Now will be updated by 8, and the goal the same, because this goal is the same. When I use 8, the goal rules 13 and 14. 13 and 14. I will select first one, 13. 13 will go to the 3. 3 will be updated from 8 to 3. Now, 3 is 5 and 6. 5 and 6. I would select 5, the first one, 5, because this is first one. 5 will be 4. Will be go to the location 4. Now, location 4 in the 7 and 8 rule. 7 rule and 8 rule. 7 and 8. And I will select first one, 7. 7 will produce 9 square. 9 will be updated in the current memory to the 9 location. 9 will fire in 2 rules, 15 and 16. 15 and 16. 15 and 16. I will select 15. 15 will be like on the square, 8 will be changed to the location 2. And the new location will be updated to 2. Now, 2 equal to the goal. It is false. And this implementation or the flowcharts of implementing this algorithm. This is working memory, and this is projections, that's mean rules, and this conflict means select first one to be implemented, and these conditions will be implemented to either continue the recursion or hold the algorithm, or halting the process. But move X Zs. Here, the Zs use it to be changed between X in the path here, and will be X here, the Zs. That means this Z will be this X here, and continue recursion this operation. For example, I will implement this. The first one will be, the first one will call path X will be 1, and the target will be 2. Now I will go to implement this process. Path X, Y, X will be 1, and this will be 2. Here move will be 1, and this is Z. Which one? I will implement first one. That means will be move Here will be move. X will be 1 and will be 8. Now I will change the Z's here. Z will be 8. And here will be path 8, 2. X 8 and this 2 equal, not equal, will be recursion. Here will be x8. Path 8, 2 will be, this is x and it is still z. Which 8 one? I think the rule 13 and 14. I will select 13. 13 will be 3. Now will be 3 and this is will be 3 because this is 3. 3 equal to, no, I will be the question out of 2, 3, this is 3 and 2, this is 3 and continue. Which one will be implemented in the 3? 5 and 6. I will be choose 5. That means 4. Z will be 4. And change it here will be path 4 and 2. And so on until I get the Z will be 2. Thus X will be 2 equal to will be false. This is the implementation of these protection rules by using flowcharts. Protection systems are capable of generating infinite loops where, or when searching a state space graph. Looping may be appear in the execution of the systems, but it cannot easily be found from the syntactic inspiration or inspections of the rule set. For example, with the move rules of the night tour problems ordered as in table 6.1 and conflict resolution strategy of selection first match the patterns of move to X with match with move to 8. That's X will be 8. Indicating a move to square 9. On the next iterations, the patterns move 9 to X would match with the move to 9 to, taking the set back to the square 2, causing a loop. Now this is process represents the same operation when we use the closed list in the searching algorithm. That preventing the loop operation. To prevent looping, pattern search checks a global list closed of visited states. The actual conflict resolution strategy was therefore select the best matching move, that list and visited states. In a production system, the proper place for the recording such game-specific data list of previously visited state is not a global closed, but working memory, but the working memory itself. Now we can alter the path predicate to use working memory for loop detections. The updating of the working memory is the same process of the using of the closed list. Assume that our predicate calculus, language is augmented by the additions of the assert x. The assert, that means the updating, the new operations by x value, which causes its arguments x to be entered into the working memory. Assert is not a binary predicate, but an action that is performed, hence it always succeeds. Assert here will be used to altering the value in the working memory. Assert is used to place marker working memory in working memory to indicate when a state has been visited. This marker is represented as unary predicates called pin X. Pin X here, that when it happens, that will be in phases we reaching this node was visited at the previous time, which takes as its argument squares on the port. Pin X is added to the working memory when the new state X is visited. Complex resolution may then require that pin Z must not be in working memory before move X for Z. Can find. For a specific value of Z, this can be tested by matching a pattern against working memory. The modified recursion path control for the protection system is for all X path X. I will use asserting predicates here. Path XY for all XY, path XY imply there exists that Z such that move from X to Z and not be in Z. Being Z, if found, that means visited. Z was visited. But when I use not being, that means Z was not visited, because not will be change the value of the truth value to the negative value, and that means is it true? And if it's correct, I will be continue assert being Z. That means if being Z not visited, now make it or marker it as visited by asserting it, assert being Z. And path ZY. Now path ZY will be changed here because X will be Z. The duplication Z here will modify X here. And this dimension is move X Z succeeds on the first match with the move predicate. This binds a value to Z. If pin Z match with the entry in working memory, not pin Z, will cause failure. Not be failure. Pattern search will then backtrack and try another match for the move XZ. If square Z is a new state, the search will continue with the pin Z asserted to the working memory to prevent future moves. Thus, the presence of pin predicates in working memory implements loop detection in these protection systems, and this will be prevent the loop from happening another time. We may generalize the night tour solution with the 8x8 square chessboard because it makes little sense to enumerate move from such complex problem. We replace 16's move part with the set of 8 tools to generate row of legal night moves. These moves predictions correspond to the 8 possible way night can move, as like in figure 6.2. 6.5, like this, with the 8 correspond to the 8 possible ways. If we index the chessboard by row and column numbers, we can define projection rules for moving the knight down 2 squares and right 1 square, like this. This condition and this action. Conditions will be consist of the current row F. That means if current row less than or equal 6 and current column less or equal 7. If this happens, the conditions of the action will be a new row will be, that's updating in new row, equal current row plus 2, and updating a new column will be current column plus 1. 2 row and 1 column. This is row. I will play this whole operations. We use predicate clause to present predictions. Then a particle could be defined by the predicate squares R and C. This is mean R mean row and C is mean column, represented in the R row and C columns of the form. The above rule could be written in the predicate calculus as like this: move square row column square new row and the new column imply that means less than or equal row and 6. That means row less than or equal 6 and new row will be row plus 2, like this predicate. And this predicate means that if column less than or equal 7 and updating the new column will be column that means current row column plus 1. Now plus is a function. This is function. This function for additions. And less than or equals and equals have the obvious arithmetic interpretations. 7 additional rules can be designed that compute the remaining possible move. This rule replaces the move part in the 3-3 version of the problem. Now, in the example of the financial advisors, we will implement a financial advisor at the production systems. The production system provides a natural vehicle for implementation. The implication of the logical description from the production scan or discount specific information and individual salary, dependents, and so on. It is loaded into working memory. Individuals, salary, and dependents loaded to the working memory. The rules are enabled when their premise are satisfied. And a rule is chosen from the complex sets and fired, adding its conclusion to the working memory. This continues until all possible subdivided conclusions have been added to the working memory. This is examples of the using advisor, financial advisor by using production system. Now, other topics: controls of search in production system. The control search. I will use 3 controls. This one is the control through choice of data-driven or goal-driven. And I will use control for searching through rule structure and use control of searching through conflict resolution. The first one, data-driven search. That means I will begin from the data. I will put the data in the working memory. And I put the goal in the working memory. And I continue using the other rules and conflict or the firing rule until I continue updating the data in the working memory until I reach this data equal to the goal. Beginning with the problem distribution, such as the set of the logical axioms, symptoms of an illness, for example, illness, or a body of data that need interpretations and infers new knowledge from the data. This is done by applying rules of inference, legal rules in the game, or other state generation operation to the current descriptions of the word and adding the results of the problem to the problem descriptions. When I apply the rules and get the goal or the protections or the results of applying these rules, I will use this result to be added in the working memory. This process continues until the goal state is reached. The current state of the board, data that have been either assumed to be true or deduced as true with the previous of the production source, is placed in working memory. The recognized as act cycle then match the current state against the ordered state of the productions. When these data are unified with the conditions of one of the production sources, the actions of the productions adds a new piece of information to the current state of the work. All the productions have the four conditions action. When the conditions match some elements of the working memory, now conditions matched with the working memory, its action is performed in recursive form or in inverse fashion. From the conditions and from the action, I will looking for this action. Which one will be implement this action in the working memory? And then I will use its conditions as a new value to update it in the working memory. And adds assertion to the working memory. Then the act of declaring a rule can correspond to an application of the inference rules modus ponens. This creates a new state of the graph. Now looking at this example, this working memory, conflict set, rule 5. I will begin from the data, because I data driven. From the data, start. And I get, which one will be used here? 6. Will be 6. Only one I will fire 6. 6 will be with V. RQ will be added to the memory. VRQ will be added to the working memory. Now, which one of them will be applied or be matched with the conditions parts? Here, V, this is here. And RQ, only V. Thus, I will be use only 5, which was only V here. Here will be added to the, and this value is S, added here. Now, from all these values, which one we implemented? Will be implemented by 2, R and S, because it's called RS. And RS will produce P. P will be added here. Now, from this, which one we implemented? P and the Q, P and the Q here. And with the implement flow, and this is the result flow, I reach the goal of the process. And the direction from the data until I reach the goal. And this production set, and this is the present the diagram or picture. The conflict resolution strategy is a simple one of the choosing the enabled rule that has fired less recently. In the event of ties of the first rule is chosen. Execution holds when goal is reached. The figure also presents the sequence of rule firing at the stage of focusing in the executions along with the graph of the space searching. Now goal-driven search. The other part, goal-driven search. Begin with the goal and work backward to the parts of the problem to satisfy the goal. To implement this as a protection system, the goal is placed in the working memory. Now, in this manner, the goal-driven, I will begin by putting the goal in the working memory. But in the data-driven, I begin with the use data in the code. Here, the implement protection system, the goal is placed in the working memory and matched against the action, not conditions. by action of the production rules. The actions are matched just as the conditions of the productions were matched in the data-driven experiment. All production rules whose conclusions, actions match the goal from the complete sets. When the actions of the rule is matched, the conditions are added to the working memory and become the new sub-goal states of the search. The new states are then matched to the actions of other production rules. The process continues until facts are found, usually in the facts. And the search stops when conditions. Supporting the production files in the backward fashions that lead to goal are found to be true. Like this, I will begin for the goal, not data. I will begin from the goal here. But in the data-driven, I begin from the start. Now I will begin from the goal, because I will begin from the goal-driven. Now goal, which one satisfies this goal? Only the first goal. I will put here in the copy set. Because it's only one rule, therefore it will be fired and one. When I fired one, which conditions will be implemented? P and Q, and added to the working memory, P and Q. Now, P and Q, which one will be implemented? P, Q. These three rules, 2, 3, 4, will be added to the here. 2, 3, 4. I will select first one. Why I am not used when 1? Because when it's visited, I will choose the second one. It's 2. 2 will be prepared R and S, and will be put here R and S. Which one is S here? 5 will be put 5. 5 will be used, will be produced the conditions and will be put B. B, which one? B, R, Q, and S. And will be stars. Because R, B, R, Q here found R, Q, and B will be stars as we hold the operation. The production rules are the encoded sets of the inferences, the knowledge in the rule-based of expert system for changing states within the graph when the current state of the word sets of a true statement describing the word and match the conditions of the production results of the and this match causes the actions parts of the rule, and this match causes the action part of the rule creates another good descriptor for the word. It's referred to as data-driven search. And alternatively, when the goal is matched against the actions part of the rules in the production rule sets, and their conditions are the sets as sub-goals to be shown to be true, the result is goal-driven problem solving. Now, the other topics are which control of search through rule structure. Now we focus about the rule structures. The structure of rule in production systems, including the distinction between the conditions and the action. As we're talking about there in the production system, consists of the two parts, conflict rules. First one is the conditions, and the second one is the action. And the order in which conditions are tried determine the fashion in which the space is searched. Now, we'll be in this control, we will focus about the ordering of the rule. Predicate calculus was simply defined through relationship in the problem domain and make no assertion about their order of the expression. Thus, an individual rules might be for all x, who x, and go x, imply mu x. And the rules of the predicate calculus. An alternative form of the same rule is for all x, who x, imply mu x, and or not go x. These two rules are equivalent. logical equivalent. But practically, it's impossible. Although these correlations are logically equivalent, they do not lead to the same result when interpreted as the prediction, because the prediction system imposes an order on the matching and firing of the rules. Thus, the specific form of the rules determines the ease of matching a rule against a problem instance. Now, the third topic, controls of search through conflict resolution. Now, which one of the rule will be used as the final rule here? The control here focus about the how I can select which one of the rules to be firing rules. What's the criteria that we use it to select first one or second one or so on? There is someone conflict resolution strategies supported by OPS5, the Prof and Turtle at 1985 include refraction. Refraction means specifies that once a rule has fired, it may not fire again until the working memory elements that match its conditions have been modified. This discourages looping. And other manner, recency. The recency strategy performs rules whose conditions match with the parts most recently added. Which one be added the first will be implemented to working memory. This focuses the search on the single line of the reasoning. And the third manner, specificity. This strategy assumes that it is appropriate to use more specific problem-solving rule rather than to use a more general one. One rule is more specific than another if it has more conditions, which implies that it will match fewer working memory patterns. Now we're talking about the advantage of production systems for artificial intelligence. The first advantage is the separation of the knowledge and control. Control is provided by the recognized act cycles of the production system loops and the production of the problem solving. Knowledge is encoded in the rule themselves. The advantage of this separation includes case of the modifying the knowledge base with the requiring change in the code of the program control, and conversely, the ability to alter the code for the program control without changing the set of production rules. I will be changing only the written code instead of the changing the working memory. Now, the second advantage, the natural mapping onto state space set. The successive states of the working memory from the nodes of the states graphs. The production rules are the sets of the possible transition between states. Conflict resolution implementing the selection of the branch in the safe space. This will simplify the implementations, debugging, and the commutation of the search algorithms. The third one, modularity of production rules. An important aspect of the production system model is lack of the syntactic interactions between production rules. Rules may only affect the firing of defined rules by changing the patterns in working memory. They may not call another rule directly as if they were subroutines, nor may they set the value of the variables in the other production rules. The scope of the variables of these rules is confused in the individual rules. This syntactic independence supported the incremental development of expert system by successively adding, deleting, or changing the knowledge of the system. And for advantage, pattern-directed control. The problem addressed by programs often require particular flexibility in the program execution. This goal is severed by the fact that the rules in production system may fire in any sequence. This expression of a problem that makes up the current state of the world determine the complex set and consequently particular set path and solution. The fifth one, tracing and explanation. The majority of rules and the interactive nature of their executions make it easier to trace execution and of a production system. At each stage of the recognized act cycle, the selected rule can be displayed, and this is manner will make avoiding to be stocking in the error mistake. Because each rule corresponds to a single chunks of the problem-solving knowledge, the rule content or can provide meaningful explanation of the system, current states, and actions. And sexual language independence. We describe the prediction tools and predicate calculus application of the form A apply B, where the truth of the A and the inference rule models comments will allow us to conclude B. That's mean if it's true A, I will get B. Although there are many advantages of using logic as part of the basis of the representation of the knowledge and the source of the sound inference rules, the production system models may be used with the other representation. I think we will finish this